Okay, so here we're looking at a pendulum in the context of conservation of energy. Basically, in these introductory physics classes, you're either going to look at a pendulum in terms of its oscillatory motion with the equations of motion given for a simple harmonic oscillator, or, like this problem, you're going to look at energy. Okay? All right, so what is the question? A pendulum with attached mass and a given chord length is released from vertical deflection as shown, and we're going to assume no air drag or other forces, and we're asked what is the velocity at the bottom, so we're going to use conservation energy for that, and what is the maximum tension in the cord. So what I have written out here is the first step for part A. Okay. So we see that energy 1 equals energy 2. Energy 1 and 2 are shown in the figure over here. Okay, those are our two points. And energy 1 is entirely going to be gravitational potential energy, and energy 2 is entirely kinetic energy. We know that because the pendulum starts from rest, so we have that V1 is going to be equal 0, and we have that the potential at the bottom is 0. So in other words, our H is defined relative to a y equals 0, basically. So we have, or exactly, we have y in the positive x direction, so y equals 0 is right here at the bottom of the swing. Because it doesn't make sense to leave any potential energy. We could, right? It wouldn't change our value. We just have an offset with everything, but we'd still find the same velocity. Okay, so we want then to think about how we solve for h. So let's run through the steps of solving for h. Okay, with the given information. All right. Okay, so to do that, let me just move something around here. Put the positive y over there. Okay, and I'm just going to show how we relate that height to the angle that's given and the length of the pendulum arm that's also given. So we have right here that this length, as I've drawn it, is going to be L minus h. Okay, so that's L minus h. So now we have a right triangle where we have one side of the right triangle, one leg is L minus h, the hypotenuse is L, and we have our angle that's given right there in the corner. So we can say to find the release height h with L and theta, we see that cosine of theta is going to be equal to, well, it's going to be adjacent over hypotenuse, so L minus h divided by the hypotenuse of L. Okay? So then we can go ahead and solve for h. Okay, so I'll multiply both sides by L, so then I'm going to have L cosine theta equals L minus h. Okay, that's just our next algebraic step. And then if I add h to both sides, subtract L from both sides, so then I'm going to have h equals, or subtract L minus cosine theta from both sides. I'm going to have L minus L cosine theta. Alright, and then I can factor out that L, and so this is going to be L times 1 minus cosine theta. And this is a good general result for pendulums. Okay, so now we can use that information in our conservation of energy. Alright, so then we're going to have mg times L 1 minus cosine theta equals 1/2 mv squared. Okay, we see that we have m's in both of our terms on both sides of the equation, so those cancel out, and now we can solve for v. Okay, so as we solve for v, we're going to get that v is going to be the square root, alright, of 2, alright, times g times L 1 minus cosine theta. Okay, like so. Okay, and we can go ahead and plug in those values and see what we get. Okay, so let's go over to our calculator here. And we want to take the square root. All right, and inside that square root, we're going to have 2 multiplied by 9.8, value that we use for gravity, times our given length of the pendulum arm of 2.4 meters. Okay, and we need to insert a multiplication in there. Okay, and then we'll open parentheses. All right, and then have 1 minus cosine theta. So 1 minus cosine, and the theta we're given is 38 degrees. Right, and then we'll close up these, and then close up the square root as well. Okay, now I don't think we're in the right mode, so let's go ahead and check here. Yep, so the default was in radian mode, so we'll do that. Okay, so we've changed to degree mode. All right, and so let's go back up and recalculate that in degrees. All right, so we get 3.16. It's always a good thing to make sure you're in degree mode if you're given an angle in degrees. So 3.16 meters per second is the velocity that we get at the bottom of the swing using conservation of mechanical energy, and there's no drag or other non-conservative forces in this problem. Okay? Okay, so now we want to answer part B, which asks for the maximum tension in the cord. Okay? So the maximum tension ends up being at the bottom of the cord, but I want to show why that is. So I want to show 2 free body diagrams for the release point and the bottom, and to hopefully convincingly show that the tension is going to have to be significantly larger at the bottom of the swing. Okay, so the free body diagram at the moment of release of the pendulum. Okay, so we look like so. All right, and then we're going to have our forces acting on this. Okay, so we have a force of gravity. Okay, and we got a tension force. Okay, and so this is our force of tension, our force of gravity. We'll look at the forces in the radial direction. So I'm going to call this the plus R direction. So then I'm just going to look at F net in that direction. Okay, so F net in the R direction. Well, we're going to have a component of gravity. We'll obviously have the tension pointing in the positive direction. Okay, and then we're going to be subtracting a component of gravity. So what does that, what does that angle look like? Well, we can look here at our force vector. All right, so we'll go back into pink, and we'll draw these other components. See if we can zoom in on this a bit. Okay, so what I'll do is I'll bring this over so we can see it. Okay. Okay, so zoom in a bit there. There we go. All right, and so what do we got? So we have to draw the different components. Okay. So I'll call these 2 components. So this will be FG in the R direction, and then this one here will be FG in the tangential direction. Okay, which is the direction of velocity, right? But it's tangent to the radius. Okay, or perpendicular to the radius. Okay, and so then we want to think about what our angle is, right? Our theta. Well, we were given the theta up above, right? So we can see it's relative to the vertical, and so it's that same angle is just going to be replicated right here. So this is none other than theta. Okay. So then we can then say, okay, well in that case, we've got the component that's in the radial direction is cosine. So it's going to be FG cosine of theta, and that's going to equal 0 because there is no acceleration in the radial direction. In fact, the only acceleration is in the tangential direction. And so that actually tells us that if we did want to solve for the acceleration at the moment of release, it wasn't asked for, but if it was, then we could simply say that it's just Fg tan equals ma, right? Where m is the mass of the ball, so we use uppercase M. And so it's as simple as that. So it would just be would just be mg sine theta divided by m, so it's just g sine theta, right? Pretty cool. Okay? So, but this tells us, right, that the tension, and this is the at release, so we'll title this one. So this is at release. Okay? So, but this shows us that the tension is simply Fg cosine theta. Okay. Well, at the bottom, we have a different story, right? So at the bottom, well, now it's vertical. So it's like this. Okay? All right, so then let's think about our forces now. Okay, so we've got our force of gravity still acting straight down, hasn't changed. And we got the tension acting along the chord, of course. All right, so we have F here, F here. This is tension, this is G. Okay. And we also want to define the radial direction, basically positive. Okay, so now it's just the same direction as positive y, but we'll call it positive r. And we want to sum up our forces in that r direction. So we'd have F net r is going to be the tension force minus the gravitational force. And notice, right, that this time it's not some component of the gravitational force, it's the entire gravitational force. So when at release, the tension was equal to mg cosine theta. But now it's just equal to mg. But even more than that, well, now there is an acceleration in the radial direction because the pendulum's swinging. And when the pendulum is swinging, that means there has to be a centripetal acceleration. Well, centripetal accelerations, by definition, point in the radial direction. They point towards the center of the circle, the circular arc of the pendulum swing. So that means that we have mv squared over L, right? Where L is just replaced R. Right? That is our radius of rotation. Okay, cool. So now we can solve for that maximum tension force. So Ft max, right? And we know it's going to be maximum at the bottom because two things happened, right? Our component disappeared. So mg cosine theta just approached to mg as theta approached 0. And our centripetal acceleration grew as velocity grew. So it's got to be biggest at the bottom. And that's true of any pendulum. Your maximum tension is always biggest at the bottom of the swing. Okay? And let's label this here at bottom of the swing. Okay, and then let's solve for that value. Okay, so then this is going to be mg plus mv squared over L. Okay, and by the way, I mean, the thing we're doing here is we simply have the centripetal acceleration pointing in that direction. Okay, let's add it here as an acceleration vector to show it on our free body diagram. And okay, well, let's factor out our m. And I have g plus v squared over L. Okay. We'll plug in our value that we solved for v and the value that we know for m. Okay. So m cancel out. It had no effect on the velocity, right? If you notice above, and I didn't call attention to that, but that velocity we found would be for any pendulum that was released at, with this length pendulum arm and at that angle. In other words, it was independent of the mass. But the tension is not independent of the mass. And so let's use the mass that's given, so 6.3. All right, so 6.3 kilograms. All right, and then 9.8 meters per second squared plus 3.16. All right, meters per second, that whole thing squared, and then divided by our length of 2.4 meters, right, the pendulum arm length. Okay. So let's get that value. All right. Okay. So the value we're going to get then, let's see, do it like this. So you can see it more clearly. Okay. Plug it into the calculator here. So 6.3, and then multiplied by 9.8 plus the value that we found for velocity, and we're going to square that. All right, and then we're just going to divide that squared velocity by 2.4. All right, 87.9 newtons of tension force. All right. There we go. And if you're curious how big it was up when it was released, how much smaller, we could simply then take that mass, so just 6.3, and then times 9.8, and then multiply that by cosine of, wrong thing there. So multiply that by cosine inverse, by cosine of 38. And so we can see that at the moment of release, the tension was only 48.7. Okay, so we'll have you add that here. Right, so 48.7 newtons. Right, so the tension didn't quite double, but it significantly increased. All right, and that is our maximum tension. All right, well, thank you very much.